1831, Michael Faraday made the greatest of his many discoveries, electromagnetic induction, that a changing magnetic field can induce an electric current to flow in a wire. In 1844, the first commercial telegraph service was set up between Washington and Baltimore, using a code of dots and dashes invented by Samuel Morse, the Morse code. On March the 10th, 1876, Alexander Graham Bell made the first successful demonstration of the telephone.
Mr. Watson, come here. I want to see you.
In 1898, Sir J.J. Thomson discovered the electron, the carrier of electric current. On December the 12th, 1901, Guglielmo Marconi succeeded in transmitting the first wireless message across the Atlantic Ocean, the 3 dots of the Morse code letter S. In 1925, John Logie Baird demonstrated the first electrical transmission of pictures. Television had been invented. In 1948, John Bardeen, Walter Brattain, and William Shockley of the Bell Telephone Laboratories invent the transistor, giving the world the transistor radio and making electronic communication equipment smaller, cheaper, and more reliable, and leading some 30 years later to the invention of the integrated circuit containing many millions of transistors. The 1950s saw the rapid spread of television and the telephone network. In the 1960s, television and telephone signals were carried for the first time by satellites, such as the low-orbiting Telstar, and then Earlybird, the first of a multitude of communication satellites placed into geostationary orbit. Also in this decade, colour TV was introduced in the UK, and the first experiments were made using glass fibres to carry telecommunications signals. The 70s gave us teletext services such as CFAX and Oracle, the fax machine, and cellular radio telephones, the first of the now ubiquitous mobile phones. The 80s brought in the personal computer, and satellite TV coming directly into the home. In the 90s, we have witnessed the explosive growth of the internet and the World Wide Web. And most recently, the beginning of digital broadcast radio and television, technically the greatest advance in broadcast technology since the introduction of colour.
This has been the century of electronic communication. At its start, the telephone and wireless were in their infancy. The electron had just been discovered, and the world was poised for the start of a revolution in communication, which would change everyday life more dramatically than in all of preceding history. As this century now draws to its close, the technologies of communications and computing have converged. The original analog forms of communication have become digital and developed beyond the wildest dreams of their inventors, so that the dawn of the new millennium heralds a world of even greater promise and potential, the digital world.
Good afternoon, everyone. My name is Jeff MacDonald. Let's begin our story on March the 10th, 1876, with Alexander Graham Bell's famous first demonstration of the telephone. Bell was a teacher of deaf children, and so he was deeply interested in the transmission of speech. He wondered if sound waves could be converted into electrical signals and sent along the telegraph wires, which by this time joined most cities together, carrying Morse code signals. He was also aware of Michael Faraday's great discovery of electromagnetic induction, that changing a magnetic field through a conducting circuit induces an electric current to flow in that circuit. Bell had constructed a simple apparatus which converted the sound waves of speech into electricity and at the receiving end back into sound again. And here we've got a replica of Bell's original telephone. And here we've made a simple demonstration of how the telephone works. It has a diaphragm which vibrates when sound waves strike it, and there is a small permanent magnet attached to the center of it. There is a coil of wire over the magnet, and I can look at the voltage induced in that coil on this instrument called an oscilloscope. And so that everybody can see the display on the oscilloscope, it will be projected up onto the video wall behind me. So let's see what happens when I speak into the diaphragm, causing the magnet to vibrate inside the coil. I'll use the same words that Bell himself used on that famous occasion in speaking to his assistant, Mr. Watson, who was at the receiving apparatus in another room. "Mr. Watson, come here. I want to see you." He was Scottish, by the way. There you saw my speech waveform on the oscilloscope. But now let's see if I can make the apparatus work in reverse, converting electricity back into sound. And here I'll take my electrical signal from a modern cassette player and try to use the apparatus as a loudspeaker. It's not very efficient, so I'll hold a microphone next to it so that everyone can hear it. Here we go.
Mr. Watson, come here. I want to see you.
Yes?
1898.
It works. And so I could use 2 copies of this apparatus to carry out a 2-way telephone conversation. But you will have noticed that my speech waveform varied in a rather complicated way. However, it's an interesting fact that speech, and any other sound for that matter, can be built up from much simpler waveforms called sine waves. And here is a sine wave, and this is what it sounds like. It's what musicians call a pure tone, similar to the sound made by a tuning fork. I can vary its amplitude, making it louder, high amplitude, and quieter, low amplitude. And I can vary its frequency. This would be a low frequency, and this would be a high frequency. The frequency is just the number of complete cycles of the sine wave in 1 second. And 1 cycle per second is called 1 hertz. The frequencies in speech run from about 50 hertz at the low end to about 15,000 or 15 kilohertz at the top end. And that range of frequencies in speech is called its bandwidth. But why are those waves called sine waves? Well, you're probably familiar with the sine of an angle in a right-angled triangle. Well, in this diagram, we have an arrow of length r making an angle theta with the x-axis. If I call the vertical component of the arrow y, then sine theta in that right-angled triangle is defined as y over r. So I could write that y equals r sine theta. But now, if the arrow is made to rotate at a constant rate, and I plot y as it varies with time, I get this beautiful curve, the sine wave, and that's how it gets its name.
Good afternoon. My name is Esther Ford. Now, can we look at the speech signal in any other way than as a waveform on an oscilloscope? Well, we can using another instrument which looks very similar to the oscilloscope. Now let's have a look what happens when I put a sine wave into this instrument. Well, instead of a time-varying waveform, we get a vertical peak. Now what happens when I vary the amplitude and the frequency of the sine wave? Well, when I vary the amplitude, the peak gets bigger and smaller, which is not too surprising. But when I change the frequency, the peak moves left and right on the screen. So increasing the frequency moves the peak to the right, and decreasing the frequency moves the peak to the left. So that means that the horizontal scale on this instrument must be frequency rather than time, as it was on the oscilloscope. Now let's see what happens when I put the speech signal into this instrument. So you should notice that my speech signal covers a whole range of frequencies. Now, this range of frequencies is known as the spectrum of the speech signal. And for this reason, this instrument is called a spectrum analyzer. Now, as Jeff said, the bandwidth of speech actually runs from about 50 Hertz to 15 kilohertz. But for transmission over the telephone network, it's actually limited to 200 Hertz at the low frequency end and 3.4 kilohertz at the high frequency end. And despite this reduction in bandwidth, the speech signal remains perfectly intelligible. So we've already learnt some of the technical jargon associated with telecommunications. Sine wave, amplitude, frequency, spectrum, and bandwidth. Now I wanted to talk to you about multiplexing. Multiplexing simply means combining several signals simultaneously for transmission over the same line. And there are quite a few ways of doing this. The first of which is known by the rather daunting name of frequency division multiplexing, or FDM for short. Now, the key idea with frequency division multiplexing is that the frequency of the speech signal can be moved up or down. So just listen to my voice. As I move the frequency of my speech spectrum up, I sound ridiculous. Now, if I move it back down again, then my voice sounds perfectly normal, even though it's been transmitted in a different band of frequencies. So what this means is that we can transmit several speech signals at the same time over the same link, but each in a separate frequency band. And this is what frequency division multiplexing, or FDM, is.
So far, the demonstrations we've seen in this lecture refer to analog signals. That is, signals which can take any amplitude over a range of values called the dynamic range. In analog audio signals, for example, the signal voltage is proportional to the sound volume, and in analog video signals, to the brightness of the picture. But the title of this lecture is The Digital World. So, what are digital signals? Well, a digital signal is simply a signal which can take only one of a few values, most commonly just two. And so such a signal is called a binary digital signal. And the two levels represent 0 and 1, the binary digits, or bits for short. Now, as we shall be seeing, there are many important advantages in sending signals in digital form. But as I've just said, the audio signals from microphones and the video signals from television cameras are naturally analog. And so the next problem we must consider is how can we convert analog signals into digital ones? But before I can explain that, let me just remind you how we can count with binary numbers. If I write a decimal number, such as 17, for example, we all understand that the 1 means 110 because of its position to the left of the 7. In the decimal counting system that we use every day, we have 10 digits. These are the numbers 0 to 9. That's why it's called the decimal system, and it probably has its origin in the fact that we have 10 fingers for counting on. But suppose I only had the binary digits 0 and 1 that I could use for counting. Then how would I do it? Well, binary 0 would be just 0, and binary 1 would be just 1, exactly as in decimal. But when I get to 2, I've got a problem, because in binary system there is no symbol for 2. We would have to write 1 0, where the position of the 1 now means 1 times 2. Binary 3, or decimal 3, would then be binary 1 1, meaning 1 2 plus 1 unit. Decimal 4 would be 1 0 0, where the position of the 1 now means 2 times 2. And we could continue in this way up to decimal 7, which would be 1 1 1 in binary. And that would be as far as I could go with a 3-bit binary code. But now let's go back to that problem of analog to digital conversion, A to D conversion. In this box, I have an electronic circuit called an A to D converter. And this particular one converts an analog input voltage into a 3-bit binary output. I can look at the analog input on this meter, labeled 0 to 7, and I can look at the 3-bit binary output on these 3 lights here. So in a moment, when I turn up the input voltage, what we expect to see is the analog voltage to smoothly increase, but the binary output to count in the 3-bit sequence that we saw earlier, where 0 means a light is off and 1 means that the light is on. So let's see if that's what actually happens. 0, 1, 2, 3, 4, 5, 6, 7. That is analog to digital conversion.
So we've now seen how we convert an analog voltage into an equivalent binary code. Now, in 1937, a British engineer called Alec Reeves had the idea that a time-varying analog signal, such as the speech signal, could be converted into a stream of binary codes if the waveform was sampled at regular intervals and each sample converted into a binary code. And this process has become known as pulse code modulation, or PCM for short. Now, the following graphic explains what I mean by pulse code modulation. So it shows a time-varying waveform, and the amplitude of each sample, which is taken at regular intervals, is converted into the binary codes shown along the horizontal axis. So let's see that in action. Here we go. So an amplitude of 7 is converted into 1, 1, 1. An amplitude of 2 is converted into 0, 1, 0, and so on. So in this way, we can convert a time-varying analog signal into a series of binary digits, or a bit stream. But at the receiving end, of course, we must convert that bit stream back into a copy of the original analog signal so that we can hear it. So how is this done? Well, the answer is quite simple. What we must do is take the binary code representing the amplitude of the signal at a particular time and convert that into an analog signal with that amplitude. And we do that with a digital to analog converter. So here I have a digital to analog converter which has a 3-bit input, which is taken directly from the 3-bit output of the analog to digital converter that Jeff showed you earlier. So just watch what happens when I increase the input to the analog to digital converter. So the output of the digital to analog converter follows the input, but now in steps, each step corresponding to an interval in the binary code. The binary codes are once again shown on the lights. So this is essentially what happens in a pulse code modulation communication system. Now, the following graphic will show a representation of the demonstration. And you'll notice that we have the 3 bits passed simultaneously between the 2 converters. So we have a 1-to-1 connection for each bit, and that's called parallel data transfer, which is a much faster way of transferring data than in serial form, where the bits go one after the other down the same line. Now, actually, both methods are used quite commonly. For example, a personal computer sends data to the printer via the parallel port, whereas it sends data to the modem, which connects the PC to the telephone network, via the serial port. Now, one interesting fact about pulse code modulation in telephone systems is that although we have used 3-bit digitization in our demonstration, for a real telephone network, for better accuracy, 8-bit digitization is used. So that means that when you're talking on the telephone, your speech signal is sampled 8,000 times every second. Each one of those samples is converted into an 8-bit code. And so you are generating a bit stream of 64,000 bits per second as you speak. Quite an amazing thought.
So we've now seen that signals such as speech can be sent in digital as well as analog form. But we've also seen that this is a much more complicated process involving sampling, digital encoding, and then decoding back into analog form again. So why go to all the extra trouble of doing it this way? What are the advantages? Well, here they are. Simplicity, switching, noise immunity, time division multiplexing, storage and copying, and processing by microchip. We'll now explain each of these terms in turn, starting with simplicity, by which we mean simplicity in transmission once the signal is already in digital form. Because in an analog communication system, it's very important that the voltage at the receiving end should be exactly proportional to the voltage at the transmitting end over the whole dynamic range of the signal, so that there's no distortion. But in a digital communication system with only 2 levels to transmit, we only require 2 distinct levels at the output, and that's clearly a much simpler thing to do.
So the second advantage is switching. Now, if you want to make a telephone call to any one of the millions of telephones around the world, then a very sophisticated network of switches is required. Now, originally, all of these switches were mechanical, which obviously required constant maintenance. But since electronic technology has developed, it's made sense to convert all of those mechanical switches into electronic ones. But a stumbling block for that is that an electronic analog switch is a very difficult thing to make. But an electronic switch for switching binary data streams is very easy indeed. So this diagram shows what is called an AND gate, a circuit that is used to switch binary data streams. Now, you'll notice it has 2 inputs, A and B, and 1 output. And the way it works is that if both of the inputs A and B have a binary digit 1, a high signal on them, then a binary digit 1 also appears on the output. If either A or B is 0, then nothing appears on the output. So we can take that a step further by saying that if we put a binary data stream on input A, then provided input B is 1, then exactly the same data stream will appear on the output. Of course, if input B is a 0, input B being the control port, then absolutely nothing will appear on the output regardless of the data stream on A. So this circuit enables us to switch binary data streams on and off, so we can make complex but highly reliable switching matrices very easily and cheaply indeed. And this is probably the most important advantage that digital has over analog.
Now, what do we mean by noise immunity? Well, unfortunately, in all electronic systems, there exists a low-level random voltage called electronic noise, which contaminates the signal and is particularly troublesome when the signal itself is small. Here we see an analog and a digital signal, and below, the same signals contaminated by noise. For the analog signal, there's very little we can do to remove the effects of the noise. But for the digital signal, we can sample at the middle of each bit and then take an electronic decision as to whether a 0 or a 1 has been sent, depending on whether the signal is above or below a certain level. If the noise voltage is not too great, then these decisions can be made with very few errors. And we can reproduce the digital data as if no noise was present. And this is what we mean by noise immunity. But if the noise voltage is much greater, then many errors will be made, and the output signal will be seriously corrupted. So a digital communication system tends to behave either near perfectly or not at all. But under those noise conditions, the analog system itself would also be unusable. Well, we can demonstrate this effect on both audio and video signals. Let's see how a real PCM system is affected when the signal is contaminated by noise. Here I have a PCM encoder and decoder, and just like the ones at your local telephone exchange. In this demonstration, we're going to inject a sine wave signal from this box here into the encoder, and we'll be listening to the output from the decoder as we contaminate the signal with noise to see what the effect is. But to help me with this demonstration, I need an assistant, and I believe that we've had a volunteer from the audience who's going to help me. Good afternoon. Welcome to the Faraday Lecture. And what's your name?
Lorraine.
You're Lorraine. And what school are you from?
Copthall School in Mill Hill.
Copthall School in Mill Hill. Have you got any friends here today? Oh, very good. Lots of friends. Okay. Well, would you like to just stand by the side there and face the audience? And you can see that you've got two controls. There's this box here, which is a noise generator, and when you turn the knob in the direction of the arrow, you'll be increasing the amount of noise injected into the signal. And you've also got a switch to operate which says digital and analog. So I'll switch the system on so we can hear the output. What position is the switch in at the moment? The switch is digital or analog? Yep. Analog, thank you. So turn up the knob to maximum, slowly and gently. And you're now hearing the noise contaminating the signal. Is that at maximum? Sure. It's now quite difficult to hear the signal down in the noise, so turn it down again, Lorraine. And switch now to digital. This time we're injecting the signal, the noise into the signal going between the encoder and the decoder. Turn the noise right up again to maximum. That's great. We're not hearing any noise this time, and that's because the system is rejecting the noise. It's immune to the noise that we're adding to it. So just to prove that we're not cheating, Lorraine, can you switch back to analog? And that's how noisy the analog system would be under the same conditions. So that's terrific. Well done, Lorraine. Thank you. Right, we'll now demonstrate the same effect on video signals, and for this we're going to need an analog and a digital TV picture, and that's what you can see on the screen behind me. The digital picture is the one on the left, analog on the right, and you can ignore the small inset diagrams which give details of how the signal is being modulated. But as you're watching those pictures, noise is being added equally to both of the signals. And so you're now starting to see, I think, that the analog picture is becoming a little bit grainy. Remember, this is video noise we're concerned with. You will see the effect rather than hear it, as we did before. And now I think it's quite noticeable that the analog picture is getting less clear than the digital one. And as the sequence progresses, the analog picture gets worse and worse, and just before the sequence ends, which corresponds to the digital picture failing, the analog picture then has got really very unpleasant to watch. And I think if that was your television at home, you'd not be very happy with it, but there we are. At that noise level, the digital picture remains perfect.
So number 4 on our list is time division multiplexing, or TDM for short. Now, that's a bit of a mouthful to say, but it's really quite an easy idea to understand. Now, you'll remember that multiplexing means transferring several signals simultaneously down the same line. And we saw earlier that we could do that for analog signals by frequency division multiplexing. Well, we can do exactly the same thing for binary data streams. But instead of interleaving them in frequency, we interleave them in time, and hence the name time division multiplexing. So I'm going to be doing a demonstration of time division multiplexing, and I believe we have 2 volunteers to help me with this. Lovely, please do come up onto the stage. Great. Yeah, big round of applause, please. Come up and join me. Okay. Hello, do you like to come and stand this side? So your name is?
Michaela.
Michaela, and which school are you from?
Copthall.
Copthall, okay, and? Popular. And your name is?
Tom Sean.
Tom. Right, and your school is?
Glenthorne High.
Glenthorne High. Wow. Okay, wow, what a response. Okay, well, Michaela and Tom are going to help me demonstrate time division multiplexing using the equipment that you can see behind us. Now, what we're going to be doing is transferring two binary data streams from the transmitting end to the receiving end. And so Michaela is going to be my multiplexer, and Tom is going to be my demultiplexer. So Tom, would you just come stand just over here for me? Thanks. And Michaela, if you follow me around, and if you just stand there, it's probably best. Thanks. Okay, so I'm standing at the transmitting end. And you can see that we've got two binary data streams, each consisting of a series of ones and zeros binary digits. And we've colored them red and green to help you distinguish them. Now, what's going to happen is that these blocks will be transferred by interleaving them in time on the conveyor belt, and then taken off and demultiplexed and put into their original sequences on these two shelves here. So, Michaela, my multiplexer, what you're going to do is multiplex these blocks in time using these clock signals, okay? Yeah, they're right up here, okay? So, red light and a green light, and they go alternately. And every time a red light is on, I'd like you to put a red block on the belt, and every time the green light is on, put the green block on the belt, okay? And it doesn't look fast, but I find it is, so you need to keep a really good eye on those clock signals, okay? And Tom, at my demultiplexing end, every time a block comes to the arrow, if it's green, if the block is green, put it on the green shelf, and if the block is red, put it on the red shelf. Okay. Okay, are you all right with that? Yeah? Yeah? And you, Michaela? Okay, Tom, if you stand here, that's easier. And Michaela, if you stand here, that's great. Okay, are you ready? Yeah. Right, steady? Go. Green. Red. Green, yes, that's good. Red. Green. Red. That's it, you're getting the hang of it. Good. You'll notice that the rate of putting the blocks on the belt is the same as the rate of taking the blocks off the belt, which means that the system is synchronized. That's a very important point. You're doing a grand job. That's working very well. Excellent. Right, the multiplexing is finished. Well done. And Tom's almost finished as well. Great. Lovely, lovely. You've done a grand job. Right, I'm just going to come and join you around the front. Okay, Michaela and Tom, can you come and join me in the middle? Either side of me. Great, thank you. Now, so Michaela and Tom have done a very good job of transferring those two binary data streams from one end to the other. Now, Michaela, was that quite difficult? Was it fast for you, or?
No, it was all right.
It was okay. Okay, well, I'm going to disappoint you, I'm afraid, because you put one block onto the belt every second. Now, in a real system, of course, the multiplexing switches work at rates of billions of switches per second, so you'll have to work a bit harder next time. Now, another difference, of course, is that Michaela and Tom transferred two binary data streams. But in practice, many more than that can be transferred down the same link, and so time division multiplexing is very efficient. So Michaela and Tom, thank you very much indeed. Round of applause, please. Next, I'm going to show you graphically what we've just done. Now, a switch at the transmitting end selects bits alternately from the two data streams and multiplexes them together in time down the same link. And at the receiving end, a demultiplexing switch takes the bits off the same link and puts them in their original orders of binary digits onto the two receiving links. Now, the reason this works is because the system is synchronized. Now, of course, in reality, we can't actually color binary digits red and green. So I'm just going to show the graphic once again, but without the colors. And it works just as well because the system is synchronized. Here we go. Lovely. Okay. And one last point I'd like to make about time division multiplexing is that it's very versatile, because the data transferred over the same link can come from a variety of pieces of equipment, such as computers, telephones, and even digital television. Jeff, where are you? Jeff?
Sorry. Number 5 on the list was storage and copying. Now, if we have digital data, and if we can store each bit individually, then there's no loss of information, and we can make as many identical copies of the data as we wish. Now, although digital data comes in the form of bits, the basic unit of digital information is the byte, which is a set of 8 bits. The familiar floppy disk, for example, can hold 1.4 megabytes of data. But perhaps the best known form of digital storage at the present time is the compact disc, or the CD, which can hold either computer or audio data. In the computer form, it's known as the CD-ROM, which stands for read-only memory. In the CD, the digital data is stored as a huge number of tiny pits on the plastic surface of the disk, which is then coated with a reflecting layer so that it can be read by a laser. Here we see the pits on the surface of a CD. Each individual pit, the smallest pits, are only a micron, that's 1/1,000,000th of a meter, 1,000th of a millimeter long. The track is a spiral which starts at the center, and if you were to unwind it, it would be 8 kilometers long. On a CD-ROM, you can hold 650 megabytes of data, which multiplying by 8 is about the population of the world, 1 bit for every person in the world. And it's equivalent to around 500 of these floppy disks. Recently, CD technology has been improved even further. So by making the pits smaller, the track separation less, and by using 2 separate layers to store the data. And this new form of CD is called a digital versatile disc, or DVD. It's said to be versatile because it can hold either computer or video data. In the computer form, a DVD-ROM, it can hold 4.7 gigabytes of data, which is around 3,500 floppy disks. DVD video gives a much clearer picture than analog video recording on tape, and it seems very likely that the DVD player with re-recordable discs will eventually replace the familiar magnetic tape video cassette recorder.
Now to the last item on our list, processing by microchip. Now, all of you will be familiar with the personal computer. Now, at the heart of the personal computer is a very complicated integrated circuit called the microprocessor. Now, the same technology that is used to make the microprocessor can also be used to make special purpose integrated circuits, which can process binary data streams in different ways. Now, one very important example of this is its use in data compression. Now, as the name suggests, data compression means reducing the amount of data to be sent, but without actually losing any information. And I can best explain that by means of an example. So in a moment, you'll see, here we go, a string of letters. Now, just for an example, the letters could represent the brightnesses of adjacent elements or pixels in a photograph. Now, we can actually encode that much more concisely. So, for example, if I had a special symbol such as an asterisk, then instead of having 6 A's at the beginning of that stream of letters, I could write A*6, standing for a string of 6 A's. So it's quite easy to see how that reduces the number of letters to be sent, but without reducing the amount of information contained in it. Now, this type of coding is quite commonly used, and if it's used, for example, for fax machines, it's called run-length coding. If alternatively, it's used for encoding computer data for storage on disks or transferring over a network, then it's called zip coding. But the most topical example of data compression is its use in TV pictures. because the data compression methods developed in recent years have made digital TV possible.
Two international groups of experts have agreed on the compression methods to be used for still and moving pictures. The Joint Photographic Experts Group, JPEG, have set the compression standards for still pictures, and the Moving Pictures Experts Group, MPEG, have done the same for digital TV and video on PCs. Now, the detailed working of both JPEG and MPEG compression is very complicated indeed, but we can explain some of the basic principles to you quite simply. Starting with JPEG, the compression method used for still pictures. The first step is to break the picture up into blocks of 8 by 8 pixels, as shown here. Now we get to the clever bit. It turns out that the picture content of each of those blocks can be built up by adding together certain combinations of standard patterns of pixels. There happens to be 64 of these patterns, the same as the number of pixels in each block that we're trying to encode. And this is what they look like. Now, the interesting fact is, and this is really the secret of JPEG, that even though in principle you require all 64 of those patterns to represent the picture in each block, in practice you can get away with using far fewer than that. And so you can reduce the amount of data you have to send by just sending the information as to which patterns are required for each block. To illustrate how effective JPEG is, we're now going to show you a series of still pictures where we've gradually increased the compression by reducing the number of patterns used for each block. Here is the test card at full resolution with no compression. If we send just 16 of the 64 patterns, the picture looks like this. There's hardly any change at all. And even at 4 patterns per block, it looks like this. It's still a very acceptable picture, but you might notice that the numbers on the calendar are starting to get a little less legible. If we take the compression a stage further, then the picture quality degrades quite rapidly. At just 2 patterns per block, it looks like this, and finally 1 pattern per block like this. And everyone would agree that picture is quite unacceptable. But what this demonstration has shown is that we can reduce the amount of data in a still picture very considerably by around a factor of 5 or so before we start to notice any degradation in picture quality.
Well, what did the Moving Pictures Experts Group, or MPEG, come up with to compress the data in moving pictures? Well, remember that when you're watching television, you're actually watching a series of still pictures or frames presented at the rate of 25 per second. So the MPEG group decided to use exactly the same trick as JPEG, but only on a few of the pictures, about 1 in every 12, and then to predict the intermediate frames between those pictures. Now, I'm going to try to explain exactly how this is done. You see at the top 2 colourful pictures, which are 2 consecutive frames from a TV picture. Now, the picture below shows the difference between those frames due to motion. So in the black areas, there's no difference, and in the highlighted areas, there has been change due to motion. So you can see that most of the area of that, there's been no change at all. So there's actually very little information to send if you only send information about the changes. So MPEG does this by looking to see how complete blocks of 8 by 8 pixels move between frames, by calculating what are called motion vectors. So the motion vectors are used to predict where each block moves to in the following frame. So we're going to see in a moment a video sequence of a horse riding through a water splash. There you go. Now the horse goes backwards because it's very clever. Now we're showing it 3 times so you can really see what's going on. And you can see the parts of the picture that don't change an awful lot, and obviously most of the motion is the horse and the jockey. So next, we'll see exactly the same again, but this time with the motion vectors superimposed. So you can see, for example, on the tree, the motion vectors don't change very much. But in areas where there is a lot of motion, they become bigger and smaller, and they're rotating all the time as well, indicating how each block of data is changing between frames. Now, on this particular frame here, you can see that especially on the back leg of the horse, The motion vectors are bigger and pointing in different directions, which indicates that the back leg of the horse was moving most at that particular time. So motion vectors are what the MPEG encoder uses to predict the next picture.
So the result of all this clever trickery is that the bit rate, that's the number of bits per second in a digital TV signal, can be reduced from the raw figure of about 150 megabits per second down to only about 6 megabits per second. That's some 25 times less. At these low rates, it's possible to send up to 6 digital TV signals in the same bandwidth and with the same picture quality as just one analog signal, in what the digital TV people call a multiplex. This is the reason why so many more digital TV channels are now on offer, but a special receiver and decoder called a set-top box is necessary to separate the signals and provide suitable analog signals to drive your television, which of course remains an analog device. This picture shows the spectrum of television signals now being transmitted from the Crystal Palace transmitter here in London. It's a very good example of frequency division multiplexing, which Esther explained earlier. The 5 spiky spectra are the analog signals, that's BBC 1 and 2, ITV, in this area it's Carlton, and channels 4 and 5. But sandwiched between them are the new multiplexes of digital TV signals, and there are 6 of them there, each carrying 4 or 5 separate digital TV signals. So overall, there's something like 5 times as many digital TV signals now being transmitted from Crystal Palace as analog ones. In fact, the UK has got the world's first digital terrestrial TV service. Eventually, possibly in around 15 years or so, all the analog television transmitters in the UK will be switched off, and then only the digital ones will remain. But perhaps the next major development in television is going to be the arrival of the flat screen display, which you can hang on your wall like a picture. And such displays already exist, and here's one that we prepared for you earlier. What you notice is that it's very large, it's very flat, gives an extremely sharp picture, but most amazingly, it is extremely thin. And so you really could hang that on your wall like a picture, and that's the shape of television sets of the future. But other technical solutions to a truly digital display do exist, and you've been watching one in this lecture, the video wall. Each of those cells contains at its heart a microchip whose surface is covered with a huge number, 800 by 600, nearly 500,000 tiny mirrors, which can be switched electronically in 2 different positions, so that a bright light beam shone at that microchip can be deflected onto the screen pixel by pixel, so building up the picture. Color is then added by superimposing red, green, and blue pictures together in the usual way. The picture is very bright because each pixel is being illuminated simultaneously, unlike in conventional TV where the pixels are illuminated sequentially. So having explained these things, perhaps some of the technical aspects of digital television in this promotional video might now be familiar to you.
See that?
What?
That is the future.
What? A load of noughts and ones?
Exactly. That's digital. The future of broadcasting.
So what's so wonderful about that then?
Well, up until now, all we've had are these.
Wavy things?
Analog waves, to be precise.
Why are there 3 cliffs?
That's caused by interference you sometimes get when the wavy things,
Analog waves?
thank you, bounce off, say, the nearest tall building or anything. Whereas with digital, the interference doesn't affect the picture at all.
So how do we become digital then?
Well, soon anyone can become digital if they want to, even you.
Now there's a perfect image.
And because digital channels don't take up as much room, you'll be able to receive many more channels.
Well, you can't have too much quality TV, can you?
Well, if you...
Well, that's enough of Richard Wilson. Now I want to talk about networks. Now most of you probably use a local area network. either in your school or your office. But on a rather larger scale, digital equipment such as computers can be connected around a town or a city by a metropolitan area network. But on an even larger scale, equipment around a whole country or even several countries can be connected by a wide area network. Now this diagram shows the relation between those types of network, and you can see that they're all linked by one common factor, the ISDN, the Integrated Services Digital Network, which is essentially the digital telephone network.
So what is the biggest wide area network of them all, the network of networks? Well, I'm sure you know the answer to that. It's the Internet, which spans the globe. In fact, the Internet has been around for around 30 years now. It started life way back in 1969 as the ARPANET, a US network of many different computers that gradually expanded out to include universities and industry. But the huge growth in the use of the Internet in the last few years has been the direct result of the invention of the World Wide Web in 1989 by a British scientist, Tim Berners-Lee, working at the CERN laboratory in Geneva. Using a new computer program called hypertext, he was able to link together files on many different computers so that now a global web of linkages, the World Wide Web, exists, making huge amounts of information available to anyone who runs a web browser program on his or her PC. The recent growth in the use of the World Wide Web has been truly explosive. It's believed that at the present time there's something like 50,000 new users around the world each day.
But what do the networks which make up the Internet consist of physically? Well, most of the traffic today is carried either by satellite, mobile communications, or by fibre optic cable. And we'll look at each of these, but firstly, fibre optic cable. Well, we have a demonstration of fibre optic cable where you can see a red laser travelling along a perspex rod by total internal reflection on the walls of the rod. Now that perspex rod is about 5 centimetres in diameter, but a real fibre optic cable looks more like one of these, if you can see it well enough. Now they're very, very thin indeed, just a few millionths of a metre in diameter, about the same thickness as a human hair. Now despite the fact that they are so thin, they can actually carry huge amounts of data, 30,000 gigabits per second. Now, at the moment, there are about 3 million kilometres of optical fibre in the UK, either underground or wrapped around the ground conductors of electricity power distribution lines. Now, the latest advance in fibre optic technology is called wavelength division multiplexing. And we can demonstrate that in our demonstration by having 2 lasers, one red and one green. And because they have different colours, they therefore have different wavelengths. And so they travel independently down the same fibre. So we can transmit twice as much information down the same fibre. And that's what I mean by wavelength division multiplexing.
Now let's have a brief look at 2 new satellite systems. A few months ago, a new satellite system called Iridium came into operation, which has 66 satellites in low Earth orbit, with 11 satellites in each of 6 different polar orbits, that's passing over the North and South poles, and they can send digital data between each other. With this system, and using a special satellite mobile phone, it's possible to call anywhere, at any time, from any place on the Earth for the very first time. Bill Gates, the founder of Microsoft, is planning an even more ambitious system of 288 satellites, with 24 satellites in each of 12 different orbital planes, to be called the teledesic network. And here's a teledesic satellite. This system will be an internet in the sky, and users will have 2-way 64 megabits per second terminals, which is some 2,000 times faster than the present standard analog modems in use today.
And so to the mobile phone, which has become very popular in the last few years. Now, the mobile phone accesses a local base station. So you might have noticed the aerial masts of these base stations, especially when you're driving along the motorways. Now, each of these base stations serves a small geographical area called a cell, and all of the base stations work. And because of the cellular structure of the system is called cellular radio. Now, when you're using your mobile phone, if you move from one cell to another, then the signal from your mobile phone is automatically handed over to the next local base station. But the handing over process happens so fast that you don't even notice it. Now, it is true that at the moment there are both digital and analog mobile phones in use. But by the year 2002, the analog phones will be taken out of use. And by then, digital mobile phones will have become an integral part of the global digital telecommunications network.
So we've now had a brief look at the new technologies of digital television and digital communications by fiber optics, satellite, and cellular radio. But what new services do they offer, and how can they be used to improve the quality of life in the future? Well, the trend in recent years has been the convergence of television, video, telecommunications, and computing, so that the boundaries have become blurred and interesting new developments have occurred where they overlap. Take, for instance, multimedia publishing on CD-ROM, or video games as just two examples. Digital television offers many more channels, and this is bound to lead to major changes in the way we use television for information, education, and entertainment. Television will become interactive so that we may select a film to view when we choose, like having access to a private large video library. And sports fans will be able to choose their preferred camera angles when they're watching a game.
Tele-shopping and tele-banking will save us time.
Distance learning will play a major role in education in the future.
Telemedicine will allow doctors and surgeons to treat patients remotely.
Telecare will enhance the care of the elderly and infirm.
People can already play video games with unseen opponents on the internet in virtual worlds.
Office workers will spend some of their time teleworking from home rather than commuting and polluting the atmosphere with their cars.
Business will be conducted by teleconferencing with colleagues around the world. So travel will be less for business and more for pleasure.
But all this is describing the technology we have now. What about the future?
Well, history shows that anyone who's ever tried to predict the technological future has always got it hopelessly wrong.
Yes, and there's some spectacular examples of that. Think, for example, of Thomas Watson, the founder of IBM, who in 1943 said that he thought the world market had room for maybe just 5 computers.
Or the New York Times in 1939 at the World's Fair, commenting on a demonstration of television, saying that it will never be a serious competitor to radio because people must sit and keep their eyes glued to a screen. The average American family doesn't have time for it.
How wrong these experts were. But one thing is certain: the world's greatest inventions and discoveries always turn out to have much greater impact than their originators could ever have imagined.
Alexander Graham Bell could never have conceived that his original telephone would have spawned 1 billion offspring by the end of the 20th century.
And Michael Faraday would be truly amazed if he could see what his discoveries have given the modern world in terms of electrical power, electrical machines, and telecommunications.
So there is no doubt that we are living through a time when technology is moving faster than the world has ever known. How we use it and how we adapt to it remains to be seen. But what is certain is that the future lies with you.